Hi there, I'm Jeremy Krug, and welcome back to AP Chemistry. We're in Unit 2, Section 2 here, where we're learning about the energy between two atoms. We're going to look at ionic bonding as well, and the metallic bonding. So we have a graph here, and this shows the potential energy between two atoms, in this case of chlorine, as they get closer to each other and farther apart. And so, generally speaking, the way this works is the bond length is going to be the distance where the potential between the two atoms is at its lowest. So you might remember that from the last video. We talked about when the atoms are farther apart, they have higher potential energy. When they're closer together and actually forming a bond, they have the lowest potential energy. So this is an actual graph of that. So can you look at this graph and tell me what the bond length is actually going to be? Well, the answer is it's going to be the length, the internuclear distance, where the graph hits its lowest point, which is 200 picometers. So that's the bond length here at 200 picometers. Now, what if someone asked you what's the bond enthalpy or the bond energy between these two atoms? Well, it is the energy where it hits that lowest spot. So it's going to be about 250 kilojoules per mole. Now, some students might wonder, well, why is it not negative 250 kilojoules per mole? Well, this a negative here represents the energy that's released when the two atoms are forming that chemical bond. Forming chemical bonds will always be an exothermic process. That's why it's a negative number there. On the other hand, the bond enthalpy refers to how much energy it's going to require to break that bond. So that's why it's the opposite sign. Bond enthalpy is always going to be a positive number. So that's why it's 250 kilojoules per mole in this case. Now let's take a look at ionic bonding. As we've learned before, it's a metal and a nonmetal that form an ionic bond. And so let's take a look at probably one of our favorite ionic bonds, the one that's formed between sodium and chlorine. And we know that sodium, if you look at its electron configuration, has one valence electron. That 3s1 electron is the one valence electron in the third occupied energy level. On the other hand, chlorine has 7 valence electrons. It has 7 because we have 3s2 and 3p5. Those are the 7 electrons in its last occupied energy level. So now we know that sodium is going to tend to lose an electron, and it's going to be able to give that electron to sodium. So it's going to donate that electron, and when that happens, we're now going to have new electron configurations. Sodium is going to have this octet right here, and chlorine is going to have this nice octet state, and this is what we're going to have. We'll have two ions. Sodium will now be a positive cation, and chlorine is going to be a negative anion. Now, we know that when they're farther apart like this, just like we said, they're in the higher potential energy state, and as they form the bond like this, they get close together to form that bond, now they're in a lower potential energy state. So farther apart is higher energy, closer together in the bond is the lower potential energy state. Now the reason this works is because after the sodium, the metal in this case, donates electrons to the nonmetal, the chlorine in this case, we now have opposite charges. And as you probably already know from other science classes, opposite charges attract. Now in chemistry, this is something we call electrostatic attractions. The positives are going to attract negative charges, electrostatic attractions. And because of these very strong electrostatic attractions, ionic bonds are about as strong a chemical bond as you can get with some very few exceptions. So take a look at this one here. Sodium and fluorine make a sodium fluoride compound with a +1, -1 charge there. And it has a very high melting point, almost 1,000 degrees Celsius. That's a very strong bond there. And how about magnesium with fluorine? Well, that's Mg+2 and 2 F negatives, and it's even stronger. Look at its melting point. It's well over 1,200 degrees Celsius. And how about this one here? We have aluminum with 3 fluorine atoms making the aluminum fluoride compound, Al has a +3 charge, and that's balanced out by 3 of these fluoride negative ions. And guess what? Its melting point's even higher, almost 1,300 degrees Celsius to melt that. Now, you might notice that there seems to be a pattern here. There is an ascending melting point. Now, why is that the case? Well, it has to do with the fact that when the magnitude of the charge increases, the melting point increases. Now, you might remember that this is an application of Coulomb's law that we learned back in Unit 1. So, as we see in this case here, sodium chloride, it's got a +1, -1 charge differential. It has a melting point of about 801 degrees Celsius. But watch what happens when we bump it up to a +2, -2 charge attraction. We're right at 2,000 degrees Celsius. Very high. Now, what do you think is going to happen if we have a +3, -3 charge differential? It's going to go even higher, isn't it? And that's what happens when you have something like aluminum phosphide, +3, -3. Look at how high that melting point is, well over 2,500 degrees Celsius. Now, because of this, we can actually predict the relative melting points of compounds by looking at the charges in the ionic compound. So in this example here, which of the following compounds would have the higher melting point? Lithium chloride or magnesium chloride? Well, look at the charges. Lithium and chlorine are +1, -1, aren't they? Whereas magnesium chloride would be +2, -1. So we have a higher charge differential on this one, so magnesium chloride has the higher melting point. If you don't believe me, of course, you can look it up online, Google it, or look it up in the chemical literature, and you'll see that the melting point of magnesium chloride is well over 100 degrees Celsius higher than lithium chloride. So that's one way to predict relative melting points. Now, what do you do if the charges of the ions are the same? Let's say that you have 3 compounds, 3 ionic compounds, and they're all +1, -1. So let's take a look at these here. We have some cases like that. Here's lithium fluoride, +1, -1, and there's its melting point. Here's sodium chloride, +1, -1, there's its melting point. And here's potassium bromide, and there's its melting point. Do you notice a hierarchy in this one? Hopefully you notice that it comes down to not the charge in this case, but it is the ionic size. Melting point decreases as ionic size increases. Hopefully that makes sense as well. That's the D part of Coulomb's law. There was a Q, which was for charge. This is the D for distance. Because, for example, in this last example, potassium bromide, those ions are so far apart, they're not able to attract each other as much, and so their attraction to each other is just lower, and so it's easier to melt that compound. Whereas lithium fluoride, those ions are much closer to each other, and so they have a stronger attraction. It actually requires more energy to melt that compound. So once again, when you have these ionic nuclei that are farther apart from each other, the attractive forces between them get weaker. So if you're asked to predict the relative melting points of ionic compounds, the first thing you want to look at will be the charges. Larger charge magnitude means higher melting point. If it's a tie, if they have the same charge, then you look at the size. That's the tiebreaker. So let's take a look at lattice energy here. That is the energy that's released when the ions are combined into this ionic compound. Generally speaking, the stronger the force, you're going to have more energy released. So in that last example, we had lithium fluoride, and look at that. It's well over 1,000 kilojoules per mole that is released whenever you have that compound formed. Sodium chloride, the ions are larger, so there's not as much of an attraction, and so not quite as much energy is released. And then the potassium bromide, those were the big ones, right? Those were the largest ions, and so look at that. They have the least energy associated with their lattice energy. Now, let's go and predict the melting points. So let's try this one first. Aluminum fluoride versus magnesium chloride. Which one has the higher melting point? Well, once again, take a look at the charges, the actual charge differential here. So think about the fact that in aluminum fluoride, we're talking about a +3 and a -1 versus a +2 and a -1. So because of that, the aluminum fluoride has the higher melting point. Now, how about this one? Once again, look at the charges. Sodium is a +1, bromine's a -1, whereas calcium is a +2, and oxide's a -2. So a larger charge differential over here. So calcium oxide is going to have the higher melting point. Look at those charges. Let's try this one here. Strontium bromide or calcium fluoride. Well, once again, look at the charge differential there. This is a +2, -1. Calcium is a +2. Fluoride's a -1. So the charge isn't going to tell us, is it? So what's the tiebreaker? It's the ionic size. So use your periodic table to find the relative sizes of those, and you'll find that strontium and bromide are farther down on the periodic table than calcium and fluoride. So that means that these two over here are larger ions, weaker force. These are smaller ions, so stronger force. So calcium fluoride will have the higher melting point. Let's try one more. Let's try calcium chloride versus sodium oxide. Now in this one, we have a +2 -1 charge differential, and here we have a +1 -2. So basically the same. So the charge isn't going to tell us. So once again, we have to look at the ionic size. So refer to your periodic table, and when you do that, you'll find that calcium and chlorine are farther down on the table. So larger ions mean weaker force. It's going to be a lower melting point. Over here, we have, they're higher up on the table, so that means that they're going to have smaller radius, and they're going to have stronger attractions, higher melting point. So that's why sodium oxide is the answer for that one. So higher melting point. You can predict that using the charge and the ionic size. Now let's take a look at this question. In which of these two metallic chlorides would you have the higher melting point? Well, hopefully you can see that it's not going to come down to charge, because everything is a 1-to-1 ratio here. So it's not the charge that's doing anything. It's the radius. And so as we said, the ones that have the smaller radius are going to have stronger attractions. So that means that the chloride on the right will have the higher melting point. You can take a look at the explanation here. As we see here, the ions or the ion centers are closer to each other in this second compound. So those ionic attractions are going to be stronger. So that's how we can justify this, by looking at the picture there. Now, we're going to jump right into section 2.3 because this is very similar to 2.2. We're going to look at ionic bonds. Now, ionic bonds produce ionic compounds. There are some properties that you need to know about ionic compounds. They have a relatively high melting point. In those last few slides, we saw that these melting points are in the hundreds, if not thousands of degrees. That's pretty high. And they're going to be brittle when they're hit. So if you take a crystal of salt, for example, I think you know that if you hit it with a hammer or a mallet, it's going to shatter. It's not like it's going to hammer out into a nice thin sheet. They're not malleable at all. Now, later in this course, we'll actually talk about why that is. Usually, ionic compounds, if you can dissolve them in water, will conduct electricity. And that's because they have these positive and negative charges. So when you dissolve them, you have these charged particles swimming around in the water, and that's able to conduct electricity. That's why we call these ionic compounds electrolytes. And so when you see an ionic compound, it is an electrolyte. Usually, they're soluble in polar solvents. Now, we'll talk more about what a polar solvent is here in a couple of videos, but the best polar solvent, or the most common one at least, is water. So most ionic compounds are soluble in water, at least a little bit. And we'll talk more about that here in a couple of units. Normally, ionic compounds have a very orderly, repeating crystal structure called a crystal lattice. And if we were to actually zoom in on this using a scanning tunneling microscope, it is actually possible to see the individual atoms. And so here we have an ionic compound where we can actually see the anions. Those are the larger little objects here. And then the cations are the smaller ones that are kind of interspersed there. So we can see that beautiful repeating crystal lattice as we look at the actual ionic compound. Now, you need to realize that ionic compounds do not exist in individual molecules. It's not like water where there's an H2O floating around over here independently, and there's another H2O floating around independently over here, and then there's another one over here. That's not how it is with ionic compounds. Instead, they have that repeating three-dimensional crystal lattice. And that lattice, like we said earlier, is held together by electrostatic forces. So in the case of sodium chloride, as an example, this is what you might see, or something like that. Of course, this is a nice, pretty picture, but that's the basic idea there. We would have a sodium and then a chlorine, and a sodium and a chlorine. This is a very orderly, repeating crystal lattice. And you would be expected to know that the sodium ion would be the smaller one, because cations are normally smaller, aren't they? So the purple ones would be the sodiums, and the green ones, which are a little bit larger, would be the chloride ions. Now we're going to jump right into section 2.4 and talk about metals and how those work. We talked about those a little earlier, but we'll talk about those some more here. Now, we said earlier that metals do not have the electrons basically frozen or stuck to the individual atoms. Those electrons are able to move around fairly freely. And so we say that those electrons are delocalized. So here's that picture again that we saw in Unit 2, Section 1, where we have those nuclei that are in that fairly orderly pattern, but then the electrons are delocalized. They're able to move around, and that is why electricity flows through metals and metallic alloys. It's kind of like we have these positively charged nuclei in what we sometimes call a sea of electrons, because these electrons are like a sea. They're able to flow freely and move around, and that's what makes electricity. Essentially, in a wire at least, you have electrons that are able to flow freely through that wire. So this is a good explanation of why metal elements and metal alloys do conduct electricity. Now let's take a look at metallic alloys. There are two important types. The first one is called substitutional alloys. And most of the alloys that you've heard of are substitutional alloys, like brass and bronze and pewter and sterling silver and things like that. Those are going to be substitutional. So in brass, you may have a main element like copper, for example, but there's a pretty good amount of zinc as well. And so what will happen is the zinc will actually substitute into the spots where some of those copper atoms would normally be. And so that's why we call this a substitutional alloy. Different elements or atoms of different elements will actually substitute into the lattice right there. Substitutional alloys. Now, another type of alloy is called interstitial alloys. Now, the most common example of this is steel. And the way interstitial alloys work is you have little smaller atoms that stick into the spaces between the atoms, what are called the interstitial spaces. And they act essentially as a hardening agent to keep these different layers from slipping. They're able to be basically stuck in place. It acts as a hardening agent. And so in the case of steel, the main element is iron. And so these little black circles are basically atoms of iron. But in iron, if you add carbon to it, you make steel. And so these little red circles would be examples of carbon atoms that are actually getting into the interstitial spaces, acting as a hardening agent. Now, different types of steel have different amounts of carbon and different amounts of other elements as well that give it different properties. And so I'm not going to say that there's a very specific, just one recipe for making steel. There are lots of different types depending upon the type of steel that you need. Well, here we've just covered sections 2.2, 2.3, and 2.4. Hope you've enjoyed the video. Give me a thumbs up if you learned something, and join me in the next video for Unit 2, Section 5.